In this video, I want to quickly go over some principles behind the idea of unit hydrographs. So what I've shown here in the upper two panels are the hydrographs here. These are hydrographs, graphs of precipitation versus time. And underneath at the bottom two panels are the hydrographs. So the hydrographs refer to the precipitation that falls within a watershed, and the bottom hydrographs refer to the discharge of the outlet stream of the watershed. And remember that we can separate out the precipitation that falls into the part that infiltrates slowly into the ground. That's the part that infiltrates down here, and the part that runs relatively rapidly over the surface of the ground to the stream network, and that's what we call the effective precipitation. So the effective precipitation is the part of precipitation in green, and on the right I've just plotted it by itself without any of the infiltrating precipitation. So this is a graph of the effective precipitation versus time. That's the effective precipitation hydrograph. Underneath, I've shown on the left the hydrograph of the stream that we might measure at a gauging station for the stream. And I've also shown how we might have separated that discharge into the base flow below, that's base flow, and the event flow or quick flow above. And then on the right, I've just simply plotted just the event flow or quick flow without any of the base flow. So this is an event discharge hydrograph. So remember, the big idea here is that the source of this water in the event flow is effective precipitation. So these volumes of water, and I want to talk about that next, these volumes of water, these should be the same. This should be the same amount of water that's described in the effective precipitation hydrograph and in the event discharge hydrograph. But first thing I might notice here is that the units are different, just like they were different when we were using, or I should say dimensions are different, just like they were different when we were doing the water balance equation way back at the beginning of the class. Precipitation is typically measured in length per time, and discharge is measured in volume for time. So what we're going to need to do is put these into a common unit or a common dimension, and we're going to do that by calculating the discharge here of the event discharge of the stream, and we're going to divide that by the area of the watershed, and that will produce an event discharge in terms of length per time, which is the same unit or dimension, I keep saying dimension, as the effective precipitation. So when I'm comparing effective precipitation and saying that that is equal to the event discharge, I've got to produce them in the same dimensions, and I'm going to do that by dividing my total event discharge by the area of the watershed, so that now I can compare them both as a length per time. Now, the next thing I want to demonstrate to you or show you how to calculate is the fact that the area under these curves represents some quantity. In the case of the hydrograph, the area under this curve represents a total length, say inches. So for example, if we got a rainfall rate of, this might be say in inches per hour over a certain amount of time, the total amount of rainfall, effective precipitation that fell, we can express as a number of inches. Similarly, if this is the event discharge hydrograph, and the discharge perhaps was measured in cubic feet per second, and that was rushing by over a period of a certain number of hours, we could then calculate the total area underneath this curve would be the total volume of water that was due to the precipitation event. So how do we actually go about calculating that? What we actually want to do is determine the area underneath these curves. So for the hydrograph, it's usually pretty easy, because the hydrograph usually is shown like this, right? So the idea here is that we want to calculate the area under the curve. In reality, we don't have a curve. We have a bunch of discrete measurements made at different time intervals, and that's going to make it really, really easy. So the area, if we want, the hydrograph curve, if you will, would have been something that looks like this. We don't actually have that. What we actually have are, in this case, 4 discrete measurements of the precipitation over a period of time. And so in order to get the total area under that curve, so the area under the curve is equal to the total depth or length of effective precipitation. And we can get that, we can approximate that as the sum of the areas of each of these rectangles. And that's what makes it relatively easy, right? So we can say that the total area under this curve is the sum of these four rectangles. And for each rectangle, it's really easy. A rectangle, it's the width times the height, right? The width is equal to, this is some increment of time. Usually it's an hour, but it could be 15 minutes or whatever it is. And the height here represents the precipitation or effective precipitation rate in length per time. And so if we multiply the effective precipitation rate in length per time times the time increment, delta t, which is in time, we're going to end up with, the times will cancel, and we'll end up with a total effective precipitation measured in length or depth. So just to give you an example, let's say this represents here, let's say this, the effective precipitation rate was equal to 2 inches per hour. And let's say the time interval was 1 hour. Then when I multiply those together, I'm going to get 2 inches per hour times 1 hour, and that is equal to 2 total inches of effective precipitation that fell during that time period. And I do that for the other 3 rectangles, and I sum them up, and I get my total effective precipitation in some measure of length or depth. Now, we're going to do exactly the same thing for the hydrograph, for the event hydrograph. So again, we have now the hydrograph itself would be a curve that looks like this, but we're just going to represent it as a sum of a bunch of little rectangles. And for each of these rectangles, like this rectangle here, we can express its area as the product of its height times its width. And the height is the event discharge in volume per time. Its width, again, is some time increment delta t. And when we multiply the event discharge in volume per time times the delta t, the time interval in time, the times are going to cancel, and we'll end up with the event discharge measured in volume. So again, as an example, let's say that the time interval here was, let's do it in a different color here. Let's say this was 1 hour. And let's say Q here was 10 cubic feet per second. We'd need to say that the volume of water, the volume of event discharge in volume is equal to the rate, which is 10 cubic feet per second times 1 hour. And we'd have to now recognize that the time units here are different, so we'd have to convert one to the same unit as the other. So probably what I do is I'd know that 1 hour is 3,600 seconds, and so I just say this is equal to 10 cubic feet per second times 3,600 seconds. Seconds are going to cancel, and that will end up being 36,000 cubic feet. So again, this is a measure of volume that's represented by the area of that blue bar, and then we would repeat that over and over again. So we'd get the total volume under that curve, which represents the total volume of event discharge, right, as the sum of all those boxes. This, again, it should be obvious that this is sort of something that Excel is just built for, because it can do these repetitive types of calculations. And once we get that total volume, right, once we get that total volume, if we want to compare it to the total hyetograph depth, we would then have to take that total volume of discharge, event discharge, and divide it by the area of the watershed, and we would end up with a measure of the discharge, event discharge in units of length. And this then, by definition, is equal to the effective precipitation. And what we're ultimately going to do, going back to the beginning here, what we're ultimately going to do is try to get a predictive relationship between effective precipitation and event discharge. What we really want to do is measure the precipitation in some watershed and figure out the effective precipitation and then predict what the discharge will be, the event discharge will be at the outlet stream. That's the real goal in all of this, is to find that predictive relationship between the effective precipitation and the event discharge.